Hey everyone, let's talk a little bit about one of the biggest applications of spheres, and it is our planet. If you did not realize this, our planet is essentially a sphere. It's an actual oblate spheroid because of the force created by the rotation. It bulges at the equator, so the radius is actually a little bit shorter at the North and South Pole than it is at the equator, but the difference in our sense is very, very negligible. So we can still do calculations treating it as a sphere, and it doesn't really affect anything. So, our planet is a sphere. But it's kind of hard for us to represent the whole planet just by drawing a sphere, because you only see one half of a sphere at a time. You do not see the back half of the sphere. So one of the complicated things is making a map. So if you want to make a map, let's say we had South America here, and Antarctica, and then Alaska, Greenland, UK, and there's a bunch of islands up here. Okay. And Hawaii. If we look at just the globe, and obviously not all of Africa would be seen, we'd probably only get to about like Egypt-ish, and that'd be over here. But if we're just looking at the globe, this would be all we see. Like all of the rest of Asia would be behind. Much of Africa would be behind. We don't see Australia except maybe like that much. Maybe, I don't know. So we can't see the whole world as it is in one shot. So we've tried to assign a rectangular plane to the sphere. And a lot of maps, they show it as a big rectangle separated into grid lines. Now, it's not the best way to show it, obviously, because, oops, didn't mean to do that. Because then when you have Antarctica, this whole side is the South Pole. So this whole side is one point. So then when you do Antarctica down here, it looks enormous, but it's really just this distance away from one point. But that's essentially what we've tried to do. We've tried to assign a rectangular grid to a sphere. And to do that, we've made two types of lines. In spherical geometry, a line is a great circle. A line is a great circle. And the great circles that we use are ones that connect the North Pole and the South Pole. These are called our longitude lines. So these are longitude. Our longitude lines measure east and west on our on our sphere. So let's say that's England. I know it's a terrible England. There's a conservatory in England, in Greenwich. And that conservatory is the one that decided, you know what, since we're on a big sphere, why don't we measure east and west using these circles that connect the two poles? We already know where the poles are, and we know that they are on opposite sides of the circle, of the sphere rather, so there is a great circle that contains them, an infinite number of great circles that contain them. Since they're the ones who thought of this, the line through them is 0 degrees. The line through them is 0 degrees. This is called the prime meridian. So that's called the prime meridian. It's the first meridian, which is another name for a longitude line. It's pretty outdated. The only one that's used for is this one, prime meridian. So from this great circle, if you go to the right, that's going east. So that means like this one would be, say, the angle between these two circles. If you were looking top down and you had 0 degrees here, whatever the measure of this arc is, which is the measure of this angle, let's say that was 35 degrees, this would be 35 degrees east. That's how you measure your longitude lines. So this could be 35 degrees east. If you went the other way, say that's 35 degrees west. So going east on the sphere is the eastern hemisphere. Going west on the sphere is the western hemisphere. But it doesn't go all the way around, because it has to stop opposite here. Because if you go beyond this, then you're going into the other hemisphere. So this 180 degrees, that's on the opposite side of the sphere as 0 degrees. This is called the international dateline. So the opposite side of the prime meridian is 180 degrees, and that's the international dateline. And the prime meridian and the international dateline divide it into the western and the eastern hemisphere. All right, so that's longitude. So that's one way we break up our sphere. And that will be the vertical lines on this odd map. The other way we do it is what would give us those horizontal lines on that map. Well, there is one horizontal line that we have in our circle. And that's the great circle exactly at the middle, halfway between the North Pole and the South Pole. This we know is the equator. So that's the equator. This is 0 degrees. And this is the only great circle that helps us with north-south. Everything for longitude was a great circle, but for north-south, which is measured with latitude, only the equator is a great circle. We have other circles, though. There's an infinite number of lesser circles that go from the equator all the way up until the North Pole. So there's really a ton of circles like this that divide through. I didn't draw them all the way across because they're not all important. There's really 5 that are important. And we've covered one of them. One of them is the equator. That's our most important. So it's 0 degrees. From the equator, you can either go up or down. You can go north or you can go south. So there's the northern hemisphere and the southern hemisphere, with the equator dividing between them. So we have our 2 tropics, and then we also have our 2 circles. Our tropics right now, they're at 23.4 degrees north and 23.4 degrees south. They're not always like this. About every 17 to 20 years, it gains another minute. So I think it's losing right now, actually. I apologize. I think it's losing time right now. So every about 17, 20 years, it loses a minute. And you guys remember degrees, minutes, seconds from the beginning of the year. But 23.4 degrees north, this is the Tropic of Cancer. Because on the June solstice, the sky was in the House of Cancer at the time. Now it's in Taurus, but I don't believe in astrology stuff. That's just how it is. That's just what astronomical phenomenon was in the sky. The shape that they made out of a bunch of dots that they said looked like a crab was up in the sky. The southern tropic is the Tropic of Capricorn. And then we have the 2 circles. The circle up top is the Arctic Circle. It's Arctic because it's to the north, and in Greek, Arctus means bear. Arcturus, I'm butchering that word, is the Great Bear, which is the Northern Star, the North Star. I'm sorry, Great Bear is Ursa Major. It's the Big Dipper, which contains the Northern Star. So every time you look for north, you look for the North Star. That's where Arctus is. This is at 66.6 degrees north right now. And then where the Great Bear isn't is Antarctis, the Antarctic Circle. And that's 66.6 degrees south. So these are our 5 latitude circles that are important. And then the South Pole and the North Pole are each 90 degrees north and south. All right, so these are our important circles. And how we get these measures, it is based on the measures of these arcs. So this arc from the equator to the Tropic of Cancer is 23.4 degrees. The arc from the equator to the Arctic Circle, that arc is 66.6 degrees. And from the equator to the North Pole makes sense, it is 90 degrees. It's a quarter of a circle. So that's where these measures actually come from. That's how latitudes are measured. Now, what's important about these tropics and the Arctic and Antarctic circles is what they mean to our seasons. So let's say we have the sun here, and the sun is shooting out rays of sunlight. Ta-da. And then we have the Earth. All right. So, excuse me. There are 4 seasons. There are 4 seasons on our planet. Summer, fall, winter, and spring. When it changes, when it's summer, that's the first day of summer is the longest day of the year. The first day of winter is the shortest day of the year. And then there's at the equator, it's an equal parts, equal length on the equinoxes. The reason being, at the equinoxes, it doesn't look exactly like this. It would be tilted that way. But at the equinoxes, the closest point to the sun is on the equator. So the closest point to the sun is on the equator. Now, the Earth would be tilted either away from us, so the North Pole would be behind, or towards us, so the North Pole would be in front and the South Pole would be behind. And as it spins, the whole planet would get its sunlight. All right? This side would be in daytime, this side would be in nighttime. That's how it works. But the equator is closest at the equinoxes. But at the solstices, something's different. So at the June solstice, that's when the northern hemisphere starts summer and the southern hemisphere starts winter. At the June solstice, the point here, which is closest to the sun, is on our Tropic of Cancer. All right, the point there that is closest to the sun is at the Tropic of Cancer. And the sun's rays would be hitting all of this side of the circle. So it's tangent up there, and this ray is tangent down there. So that means, as it spins about the North Pole, everything in this circle is in all sunlight. And as this part spins about the South Pole, everything in this circle is all darkness. These circles are our Arctic and Antarctic circles. And this should make sense because that's our center. This point that's closest and this point down here, those radii would make a right angle. This is a quarter of a circle. Well, this was 23.4 degrees north. This was 66.6 degrees south. And if there's a 0 degree somewhere in there, it'd be about there. Well, 23.4 and 66.6 degrees south, they add up to 90 degrees. That's why their measures are actually complements of each other. And then on the exact opposite side of the Earth is the other 66.6 degrees up here at 66.6 degrees north. But that's how we measure latitude and longitude. All right. So that's a little bit of applicable spherical geometry for us. Enjoy. Oh, actually, there's one more thing I want to point out. If we look at our sphere, at our planet, if we have our equator, and then we have any longitude. Pretend that's a longitude and it passes through the bottom of the circle. These two great circles are actually perpendicular. So let's say this was our prime meridian. And let's say we also had the circle that was 90 degrees west. This longitude is also perpendicular. But then if this is 0 and that's 90, these longitudes are perpendicular to each other as well. So just a cool thing about spherical geometry that I want to show you guys before I log off is that this figure right here, well, these are parts of lines on the sphere. So that would make them line segments on the sphere. So this is a region bounded by 3 line segments. That's a triangle. And it has 3 right angles. So in spherical geometry, you can actually have a triangle with 3 right angles. I just thought that's a cool thing for you guys to see. Other than that, have fun.